My name is Sadique. I'm from Zurich, and I'm going to show you some of the things that we do in Zurich. So, what you see here is a rack. It is 3 racks of multi-neuron chips. So each of these chips here is a multi-neuron chip. It has 2,000 neurons on it, and it has about 4,000 synapses in total. Similarly, there are similar chips on the bottom 2 racks. They have fewer neurons but more synapses. And what you have is a loop that connects each of these chips to the next chip in the loop, and they're connected to this device called the mapper. What it does is it basically sends spikes and reroutes them to wherever you want them to go to, basically, right? And as part of the loop is also this sensor here. This is a vision sensor developed by Toby. This is a very early version of the sensor. It only has 64 by 64 pixels, right? So the current versions have 256 by 256. So here you see a very noisy output from this retina here. So if I move my hand, you kind of see simple figures moving there. Right, so if I move my hand from left to right, you see the corresponding motion. And if you just project this same pixel output into a linear array, and you want to look at what's happening over time, you see these black dots there, or black stripes, which is basically the same spikes that you see here, but you just spread them across over time. Right, so what I'm doing now is that I'm sending the spikes from this sensor here to this particular chip here through these cables. Okay, so I'll show you what the output of this chip here is. So now you see, when there's nothing much happening, the output is very sparse. You don't see any dots there. But as soon as I move something, you see that the chip responds. So whenever there is motion, you see a much higher response than you see here, right? So it's a very simple motion detector, if you want to call it. So if you want to, so there was a talk about how you would detect a bear next to the trash cans that keep toppling in the night, and this would be a very simple example of that, where you just take the input from the retina and then you project them onto these chips, and you detect whenever there's motion, right? So that's a very simple network. So it's really just connecting these spikes from the retina to the spikes on the other chip, to the neurons on the other chip. Now what we're going to do is, so these chips are specially built for a purpose, and that is to do a computation called winner-take-all. All right, so now what you're going to see is, what you're seeing here, in fact, is a bunch of red dots. So the red dots are the output from these chips there, okay? And you'll see some black dots, which are the same as what you'd seen before from the retina, okay? But with the difference that now the black dots are coming from my computer instead of the retina. So this is simply to demonstrate the capability of this chip, right? So what I'm doing is simply sending these black dots here, which are spikes that go over time at 2 different locations on the chip. So this axis here is the different neurons on the chip, and this axis is time. So as time flows, you see different things happening. The red dots are the spikes that are getting out of the chips, and the black dots are the input. So what you immediately observe is that there are more red dots here than here, while I'm sending black spikes at both locations. So what this chip is basically doing is it's detecting which one is the stronger input, or which location has higher spikes. It detects that, and it basically sends out a signal saying that this is the location where I have a stronger input. So now if I just flip this input and make the input at the bottom stronger, you'll immediately see that the response of the chip also flips. So now you see a higher response at the bottom. So essentially this computation is called a winner-take-all computation. And this is something we always do. So if you're having a conversation at a noisy room, for example, you want to listen to one person who you're talking to, and you want to ignore the people who are talking next to you to someone else. And this is a simple winner-take-all computation where you're trying to choose a winner and focus your attention onto this winner. Right? And this is the computation that these chips are specifically designed to do. Okay. And these networks are inspired by what people have studied in the brain. The people have observed such networks existing in cortex. And so based on those studies, we design chips that do similar computation. And we hope to understand better how brains do much more complicated tasks by implementing these networks on these chips.